We shall start by a look at the structure of an atom. Remember, we described an atom as the smallest particle of an element that can take part in a chemical reaction. In this chapter, we shall discover that an atom is not the smallest particle there is. We shall look at what really makes up an atom, and we will see that atoms of different elements are different both in structure and composition. And because of this difference, we shall arrange the elements into groups and periods to create what is called a periodic table. Remember, we also said that when elements combine chemically, a compound is formed. So if really atoms participate in chemical reactions, just how do they combine? We shall look at chemical reactions and equations. We saw in Form 1 that an element is made up of atoms, and we defined an atom as the smallest particle of an element that can take part in a chemical reaction. A closer look at an atom reveals that it is actually made up of even smaller particles that we call subatomic particles. The subatomic particles include protons, neutrons, and electrons. Structurally, an atom consists of a small part called the nucleus and a larger region surrounding this nucleus. The protons and neutrons occupy the nucleus and they are collectively known as nucleons. The electrons occupy the region surrounding the nucleus. The general structure of an atom is as shown in this diagram. In the central part, we have a nucleus which consists of protons and neutrons. Surrounding this small nucleus is the outer region which consists of the electrons. For instance, the smallest atom there is hydrogen. Hydrogen has one proton and one electron and has no neutron. Next from hydrogen is helium. Helium has two protons, two electrons, and two neutrons. So these so-called subatomic particles, just what are they like? Now, the protons inside the nucleus are positively charged. The electrons occupying the region surrounding the nucleus are negatively charged. The neutrons carry no charge. It is also true that the number of protons is equal to the number of electrons inside an atom. This means that the amount of positive charge inside the nucleus is equal to the amount of negative charge in the region surrounding the nucleus. So overall, an atom has equal amount of positive as negative charge and is consequently neutral. But this illustration is not sufficient to clearly depict what it is to describe an atom. Although no one has yet found a way to get a closer view of an atom, different experiments have made it possible to draw up a picture model of an atom. The colors in these models, of course, are used to distinguish the different particles. In the center of an atom is the nucleus, and this consists of even smaller subatomic particles called the protons and the neutrons. The protons are positively charged. The neutrons are as heavy as the protons and carry no charge. This means that overall, the nucleus is positively charged. Orbiting around the nucleus are negatively charged particles called electrons. The size of the positive charge carried by the proton is equal to the size of the negative charge carried by the electron. Now the electrons are moving at incredible speeds around the nucleus. So what prevents them from shooting in all directions? If you could pull an atom into its component parts, we'd say that it contains the same number of positively charged protons as negatively charged electrons, and it is the force of attraction between the oppositely charged particles that prevents the electrons from shooting off. Each atom is described by the number of protons and electrons it carries. A hydrogen atom has 1 proton and 1 electron. An oxygen atom has 8 protons and 8 electrons. An iron atom has 26 protons and 26 electrons. Now we turn around and look at the atomic and mass numbers. It has been shown by experiments that the mass of a proton is equal to that of a neutron. The mass of an electron is negligible. Generally, the mass of an atom is thus the sum of the relative masses of the protons and neutrons in the nucleus of that atom. The atomic number is simply the number of protons in the nucleus of an atom. The atomic number is usually represented by a capital Z. Mass number is the sum of the protons and neutrons in the atom. It is usually represented by a capital A, and hence A is given by P plus N, that is protons plus neutrons, and Z is equal to P. Therefore, given the atomic number and the mass number, it is possible to find the number of neutrons in the nucleus of an atom. For example, sodium has atomic number 11 and mass number 23. It follows that the number of neutrons is 23 minus 11, which will give us 12. Both the atomic number and the mass number of an element can be represented alongside its symbol. Taking an imaginary element with the symbol X, we can represent atomic number Z as a subscript and mass number A as a superscript. For example, sodium has atomic number 11 and mass number 23, and therefore becomes as indicated here. The others would include hydrogen, helium, phosphorus, and many others. Let us now look at something called isotopes. It was stated earlier on that atoms of the same element have the same number of protons in the nucleus. Thus, they have similar atomic numbers. Sometimes, however, atoms of the same elements have different number of neutrons in the nucleus. The consequence is that these atoms have different mass numbers. Simply stated, isotopes are atoms of the same elements having the same atomic number but different mass numbers. Elements that have isotopes include hydrogen, carbon, oxygen, chlorine, among others. The isotope is given its name alongside its number. For example, hydrogen has 3 isotopes with mass numbers 1, 2, and 3. Their names are hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 2 is also called deuterium, and hydrogen 3 is also called tritium. Unless otherwise stated, the name hydrogen shall always refer to hydrogen 1. Carbon, on the other hand, has 2 isotopes. Carbon 12, which has 6 protons and 6 neutrons. Carbon 14, which has 6 protons and 8 neutrons. Chlorine has 2 isotopes, chlorine 35, which has 17 protons and 18 neutrons. Chlorine 37 has 17 protons and 20 neutrons. Oxygen has 3 isotopes, oxygen 16, oxygen 17, and oxygen 18. Let's now look at electron configuration and energy levels. Now, we indicated that the region surrounding the nucleus is occupied by electrons. These electrons are not just scattered anyhow in this region. the electrons occupy specific zones we call energy levels. The energy levels are numbered 1, 2, 3, and so forth, starting from the one nearest the nucleus. Electrons occupying the same energy level have approximately the same amount of energy. Each energy level has a maximum number of electrons that it can accommodate. The first energy level can accommodate a maximum of 2 electrons. The second energy level can accommodate a maximum of 8, and the third energy level can accommodate a maximum of 8 electrons as well. Conventionally, electrons are represented either by a dot or a cross. In this tutorial, we shall represent electrons with crosses. Notice that the hydrogen atom has only one energy level. When the energy level has taken the maximum number of electrons it can possibly accommodate, the remaining electrons move to the next level. This distribution of electrons in the energy level is what we call electron configuration or electron arrangement. This is represented as shown here. Hydrogen has an electron configuration of 1. Lithium has an electronic configuration of 2 to 1. Sodium has 2, 8, 1. And calcium has 2, 8, 8, 2. If you add up the figures in each configuration, you get the atomic number of that element. Now, important to note is the maximum number of electrons each energy level can accommodate. And hence, you can write the electron configuration for any element given the atomic number. For example, in this table, for an atomic number 1, the electron configuration is 1. 5 will be 2 to 3. If you go to electron configuration for atomic number 10, it will be 2, 8. Atomic number 19 has electron configuration of 2 to 8 to 8 to 1. Finally, atomic number 20 has configuration 2 to 8 to 8 to 2. Now, it is important that you keep in mind that an energy level is really not a physical thing. It is rather a region or a certain distance from the nucleus around which electrons possessing approximately the same amount of energy revolve. Now, to better understand this, let's look at the lithium atom and its energy levels. Now, if you look at that, there's nothing really physical to tell you that this is the first energy level and this is the second energy level, but clearly you can be able to tell there are 2 energy levels. 2 electrons are revolving in the first energy level, which is the innermost energy level closest to the nucleus, and 1 electron is revolving in the second energy level. Now, just as a by the way, the electrons that revolve in regions farther from the nucleus possess higher amounts of energy compared to those that are closest to the nucleus. And now we turn and look at the classification of elements into periods and groups. And we start with periods. Now, depending on the atomic number, some atoms have 1 energy level, others have 2, and others have 3, while others would have 4. For example, hydrogen with a configuration of 1 has 1 energy level. Helium has a configuration of 2 and also has 1 energy level. When you come to lithium, it has a configuration of 2 to 1, and that means it has 2 energy levels. Aluminium has a configuration of 2 to 8 to 3, which follows that it has 3 energy levels. For potassium, it has electronic configuration of 2 to 8 to 8 to 1, and that means it has 4 energy levels. Now, it is important to notice that there is no empty energy level, because if you remember, we said an energy level is really not a physical a region, but rather it is a region round which electrons revolve. Atoms with the same number of energy levels are said to belong to the same period. Periods are named using Arabic numerals 1, 2, 3, and so forth. For example, period 1 has hydrogen and helium. Period 2 has lithium, beryllium, boron, all the way up to neon. Period 3 has sodium, magnesium, up to neon. Let's now turn to groups. Now consider the electron configuration of these elements. Lithium 2,1, sodium 2,8,1, potassium 2,8,8,1. So just what is so common amongst all these three atoms? You realize that the outermost energy level has one electron in all the elements. Now take a look at this second group. Beryllium 2,2, magnesium 2,8,2, calcium 2,8,8,2. Again, in this category, all the elements have 2 electrons in the outermost energy level. Elements with the same number of electrons in the outermost energy level are said to belong to the same group. Groups are numbered using the Roman numerals 1, 2, 3 up to 8. Now there are 8 groups. So do not confuse the naming of groups and periods. If you name the period with a Roman numeral, the answer would be wrong. Now in the next chapter, we will discover that elements that belong to the same group show similarities in trends of chemical and physical properties, but elements across periods will show gradual change in physical and chemical properties. Now, we have said equality in the number of electrons in the outermost energy level leads to elements being grouped together into groups. Equality in the number of energy levels means the elements are classified into periods. Now, combining the information on groups and periods, a periodic table can be drawn. Now, the periodic table for the first 20 elements is as shown here. Now, looking at this periodic table, the rows represent the periods, and we have period 1, 2, 3, and 4. The columns represent the groups. We have group 1 all the way up to group 8. It therefore means helium, lithium, sodium, and potassium all belong to group 1. Group 2 has beryllium, magnesium, and calcium. Group 3 has boron and aluminium, all the way up to group 8, which is also called group O, which has helium, neon, and argon. However, this is a very simplified version of the periodic table for the first 20 elements. Between group 2 and 3 lies a group of elements we call transition metals. These elements have unique features that make them difficult to fall under any of the first 8 groups and 4 periods as described earlier. Okay, now just how much does an atom weigh? We look at the relative atomic mass. The mass of an atom is in the order of 10 raised to negative 22 grams. Clearly, weighing an atom is a more than impossible undertaking in an ordinary lab. It is easier to express the mass of an atom in relation to another, the standard. For example, the atom of hydrogen was the first one to be chosen as a reference and was arbitrarily allocated atomic mass unit of 1. Therefore, the mass of any other atom compared to that of hydrogen is called the relative atomic mass. For example, calcium is 20 times as heavy as hydrogen. Its relative atomic mass is therefore 20. The hydrogen scale would, however, later be replaced by that of oxygen in the beginning of 20th century, but this was also later dismissed due to oxygen having many isotopes. The International Union of Pure and Applied Chemistry, IUPAC, in 1961 recommended a scale based on carbon-12. This carbon isotope weighs exactly 12 atomic mass units and is readily available. Therefore, the relative atomic mass unit is defined as the mass of an atom compared to that of carbon-12, which is 12 atomic units. Mathematically, relative atomic mass unit is equal to average mass of an atom over the mass of an atom of carbon-12. I know you're just thinking, what about in situations where we have isotopes? When it comes to isotopes, the relative atomic mass is closest in value to the mass of the most abundant isotope of the element. For instance, if an element X has two isotopes with percentage abundance S, X35 has percentage abundance of 75, X37 has percentage abundance of 25, calculate the relative atomic mass and state which is the most abundant isotope of the two. In this solution, we simply multiply each isotope mass number with the percentage abundance. We then add the two and divide by 100%. That means 35 times 75 plus 37 times 25 over 100%. If you calculate that, we'll get 35.5%. Now this value is closest to 35%, and therefore X35 is the most abundant of the two isotopes. Now that was quite simple. Now the abundance can also be given in terms of ratios. So let's look at a more complex example. If an element Y has two isotopes, Y6 and Y7, and the relative atomic mass of Y is 6.94, determine the ratio of the percentage abundance of the two isotopes. Now in this solution, assuming on a scale of 0 to 1, the abundance of Y6 is X. I'm just choosing a value X randomly. It therefore means that Y7 will be 1 minus X. Why? We are on a scale of 0 to 1, 0 being the lowest and 1 being the highest. The ratio Y6 to Y7 will be equal to X to 1 minus X. We then proceed as usual and equate to the given relative atomic mass. So 6 we multiply by X because it is the corresponding abundance according to what we have chosen arbitrarily, plus 7 we multiply by its corresponding abundance, which was 1 minus X. We divide by the total is 1, and we equate to 6.94. So normal multiplication, 6x plus 7 minus 7x is equal to 6.94. Now proceeding, minus x plus 7 is equal to 6.94. Minus x is equal to minus 0.06. X is 0.6. Now we already found the value of our x. The ratio Y6 is equal to 0.6, which means y7 is 1 minus 0.06. Remember, y7 was equal to 1 minus x, and we have already found the value of x. Therefore, y7 is equal to 0.94. Now, this ratio becomes 0.06 rather, to 0.94. Now, to simplify, we multiply each side by 100, and we shall get y6 to y7 is equal to 6 to 94. If we further simplify that, we get 3 to 47. Now, in terms of percentage, you'd realize y6 would be 6% and y7 would be 94%. Ion formation. When the outermost energy level is full to capacity, the atom becomes very stable. This means atoms with configuration of 2 to 8, 2 to 8 to 8 are very stable. They have very little tendency to change or participate in a chemical reaction. Atoms with any other configuration are very unstable and have high tendency to react. Such atoms with any other configuration can attain stability by either gaining or losing electrons. For example, consider sodium with configuration of 281. Sodium can lose the 1 electron, getting a configuration of 28, which is stable. It could also gain 7 electrons to become 2 to 8, which again is very stable. But obviously, it is easier to lose 1 electron than to gain 7. The same case follows for magnesium with 282. It would be easier for magnesium to lose 2 electrons than to gain 6. Now, consider chlorine atom with configuration of 2 to 8 to 7. It is easier to gain 1 electron to become 2 to 8 other than lose 7 electrons to become 2 to 8. The same case would follow for oxygen with configuration of 2 to 6. It would be easier for oxygen to gain 2 electrons to become 2 to 8 than lose 6 electrons to become 2. Now, let us go back to sodium. The atom of sodium has atomic number 11, which means it has 11 protons and 11 electrons. Now, if sodium atom loses the 1 electron in the outermost energy level, it means that it now has 10 electrons but 11 protons. The loss of an electron is not accompanied by loss of a proton. This will mean that it is no longer a neutral atom anymore. It has a net charge of positive 1. Protons now exceed electrons by 1. The particle formed is now called an ion. Now look at magnesium atom. It has 12 protons in the nucleus and 12 electrons in the energy levels. In forming an ion, magnesium would prefer to lose the 2 electrons in the outermost energy level. Once the electrons are lost, look at the particle that is formed. This particle has now 12 protons, just like the previous one, but in this case it has 10 electrons. Protons being more than the electrons, they exceed by 2, and therefore the particle that is formed has a net charge of positive 2. This is the magnesium ion. Now, when it comes to chlorine, it has 17 electrons and 17 protons. That is a chlorine atom. The chlorine atom, to gain stability, would prefer to gain 1 electron. So once another electron joins the energy level, this electron will join the already existing energy level. The number of electrons in this case exceed those of protons, and electrons being negatively charged means a chlorine ion that is so formed has a net charge of -1 or -1. Oxygen will gain 2 electrons to become an oxide ion. So if you look at that oxygen atom, it has 8 electrons in the energy levels and 8 protons in the nucleus. So when it gains 2 electrons, the particle that is formed, you can see the new electrons indicated by dots. Therefore, the oxide ion carries a net charge of -2. Now, the new electrons gained are represented by dots. It's also important you realize that when the incoming electrons joins, it joins, or rather occupies, the already existing energy level. The transformation that occurred in the gaining and loss of electrons can be represented by the following equations. Aluminium on its part will lose 3 electrons, like you can see here. Now, positively charged ions are called cations, and the negatively charged ions are called anions. Now, before we proceed to the next part, let's look at some of the few terminologies. And we start with the valency of an atom. Simply speaking, the valency of an atom is the number of electrons an atom gains or loses to gain stability. For example, sodium and chlorine both have a valency of 1. Remember, sodium loses 1 electron and chlorine gains 1. Both have a valency of 1. Magnesium and oxygen have a valency of 2. Now, notice that the valency is the absolute number without the sign. This valency is very important in combining elements during chemical reactions. Next is radicals. And radicals are groups of atoms that carry a net charge and exist and react as a unit. Examples of radicals include sulfate ion, ammonium ion, nitrate ion, hydroxide ion, nitrite ion, hydrogen carbonate, hydrogen sulfate, carbonate, sulfite, phosphate, and so on. Let's see oxidation number. Elements react by either gaining or losing electrons, and they therefore are said to acquire a new state. This is what is called an oxidation state or oxidation number. The oxidation number of an element shows the number of electrons gained or lost to attain its current state. However, unlike the valency, there are positive and negative oxidation numbers. For instance, sodium loses one electron to get a sodium ion. Its oxidation number is positive 1. Magnesium loses 2 electrons to become a magnesium ion, and its oxidation number is positive 2. Chlorine ion has an oxidation number of negative 1. The oxide ion has an oxidation number of negative 2. Now, note, however, that it is the charged particle ion that has the oxidation number. An atom has an oxidation number of 0 because it is not charged. Now, ensure you do not confuse the oxidation state, charge, and valency. They are quite different. So now let's look at chemical formula. Now, elements combine to form compounds. During chemical reactions, atoms of metal generally lose electrons, while those of nonmetals acquire electrons to form ions. For instance, sodium reacts with chlorine to form sodium chloride. The sodium atom loses an electron to form the sodium ion. Chlorine acquires that very electron, forming a chloride ion. Now the two ions combine to form a compound. That is, sodium ion plus chloride ion would form sodium chloride. When sodium chloride is written using these symbols, this is called a chemical formula. Now, in order to write a chemical formula of a compound, we must know 1. The chemical symbols of the elements involved and their valencies. The element that loses the electron comes first. So let's combine magnesium and chlorine. Magnesium has a valency of 2. Chlorine has a valency of 1. In writing the chemical formula, the valencies are interchanged and then written as subscript after the symbol of each element. When the subscript is 1, it is not written, and hence we are going to have this formula. If the ratio of the valencies can be simplified, then it is done so. For example, magnesium and oxygen to form magnesium oxide. Both magnesium and oxygen have a valency of 2, and therefore magnesium oxide will have both subscripts as 2. Therefore, we cancel out, leaving the formula as shown here. Look at carbon and oxygen. Carbon has a valency of 4 and oxygen has a valency of 2. The formula might be C2O4. Now the ratio 2 to 4 can be simplified into 1 to 2, and therefore we have the formula as CO2. Aluminium and oxygen. Aluminium has a valency of 3. Oxygen has a valency of 2. The formula is Al2O3 and cannot be simplified further. Remember, the symbols of the elements are retained even in the compounds. Capitals remain capitals. In combining particles involving radicals, the net charge of a radical is taken as the valency. For example, sodium ion would combine with carbonate ion, and the valencies are interchanged to form sodium carbonate with the formula shown here. If the particle combining with the radical has a valency greater than 1, a bracket is used to enclose the radical part before the subscript is added. Aluminium reacting with carbonate would have the formula aluminium 2 and carbonate, which we need to add 3, the valency of aluminium, and therefore we will put brackets and then add 3. The same thing is done when two radicals combine. For example, ammonium ion combining with sulfate ion, the bracket will come, or rather will fall under ammonia, and the formula will be as shown. Now, there are some elements which have varying valencies or combining powers. For example, copper can have a valency of 1 or 2. Now, in such cases, the valency exhibited is indicated in Roman numbers in brackets when the name of that compound is written. For example, copper 2 oxide is different from copper 1 oxide from the formulas like you can see. Carbon 2 oxide, commonly called carbon monoxide, has that formula as opposed to carbon 4 oxide. Iron 2 chloride is different from iron 3 chloride. Let's turn to chemical equations, and this is just writing the word equations using the chemical symbols. Now, in most of the remaining course in chemistry, you will be writing chemical equations unless otherwise advised. It is, however, important to know that some atoms don't exist independently but combine into molecules. For example, oxygen, chlorine, and many others. You must know the product and its chemical formula. A reaction between copper and oxygen will thus be written as shown here. Sodium and chlorine will react and the chemical equation will be as shown. Same follows for aluminium and oxygen. Now, these chemical equations are not just written for the sake of it. They must also depict the ratio of combining of those elements involved in the reaction. So we look at balancing of chemical equations. Now, when a chemical reaction takes place, nothing is lost. All the reactants must be part of the product. Consider the equation copper plus oxygen to form copper 2 oxide. Now, simply stated, one atom of copper reacts with 2 atoms of oxygen to form copper 2 oxide. Now, however, in the formula of copper 2 oxide, it suggests that there is 1 oxygen atom. So just where is the other one? In the law of conservation of matter, atoms are neither created nor lost. We must therefore balance the equation by multiplying some parts with certain factors. The multiplying factors must be in the simplest ratio. Now, in the above case, we shall multiply copper by 2, and then the product copper 2 oxide shall also be multiplied by 2. Now, this equation is therefore balanced in this case. Consider aluminium and chlorine to form aluminium chloride. This equation is unbalanced. If I multiply aluminium by 2, I multiply chlorine by 3, and aluminium chloride by 2, the equation becomes balanced. Zinc plus hydrochloric acid will give me zinc chloride plus hydrogen gas. This again is unbalanced. But if I multiply the hydrochloric acid by 2, the equation becomes balanced. The number of atoms on the left-hand side, that is the reactant, equal to those on the right-hand side, that is the product. State symbols. Now, a chemical equation is complete if balanced and the state symbols of the reactants and products are indicated. The state symbols are enclosed in brackets, and they are solids represented by S, liquid by L, gas by G, and aqueous represented by AQ. Now, aqueous means in solution. Now notice dilute acids fall under aqueous. For example, in the cases we had above, copper plus oxygen gives us copper 2 oxide. Now copper is a solid, oxygen a gas, and the product copper 2 oxide is also a solid. The same thing will follow for aluminium reacting with chlorine, as well as zinc reacting with hydrochloric acid. Now, this far we know that an atom contains subatomic particles that we call protons, neutrons, and electrons. We know that protons and neutrons are found in the nucleus and are called nucleons collectively. The electrons are found in the energy levels. Now, each energy level has a maximum number of electrons it can hold. We also know that the number of protons is equal to those of electrons, and thus an atom is neutral in charge. Atoms of the same elements we've seen have equal number of protons but may have different number of neutrons, which gives rise to isotopes. The atomic number Z is the number of protons, and the mass number A is the sum of the protons and neutrons. We've said that electron configuration shows the arrangement of electrons in the energy levels. Now, elements with equal number of energy levels are said to belong to the same period. Those with equal number of electrons in the outermost energy level belong to the same group. We've also seen that these families are key to constructing the periodic table. We also know an atom can lose or gain an electron or electrons to gain stability, and thus forms ions, which could be cations or anions. The valency of a particle is important in writing chemical formula. It is called the combining power, and it is the number of electrons gained or lost. We know that to write a chemical equation, we need to know the symbol of the elements combining. We balance the equation and indicate the state symbols. Now, going back, we also said that periods and groups form chemical families. Now, we are going to look at chemical families in the next chapter.
Choose a path, choose a direction, choose your day, choose your hours, choose to network, choose a strategy, choose to create, choose your media, choose to care, choose to inspire, choose to listen, choose to learn, choose to train, choose to compete. Newcastle College, why choose anywhere else?